Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and in this video we are going to solve another gate question. So this gate question was asked in the year 2016 for 2 marks, and this is related to CPU scheduling. So let us read this question. So the question goes like this: consider the following processes with the arrival time and the length of the CPU burst given in milliseconds, right? So this is a table, as you can see, which has the information about the processes that are there in the system. So there are 4 processes: P1, P2, P3 and P4, and these are the arrival times, right? So these are in milliseconds. Now the scheduling algorithm used is preemptive shortest remaining time first, right? And the question is asking that the average turnaround time of these processes is how many milliseconds. So basically we have been given the data about the processes, that is, these are the arrival times and this is the burst time. So the arrival time is the time instant at which the process has arrived in the system, right? And we can think of this as the time at which it has been queued into the ready queue. And the burst time is basically the total time that the process will execute. So P1 will execute for 10 milliseconds, P2 will execute for 6 milliseconds, and so on. So the burst time is the duration of execution. And the algorithm that we are going to use is preemptive shortest remaining time first. So we have already discussed about this algorithm in one of the videos. So in shortest remaining time first, when we are trying to decide which process should go on the next, should go to the CPU next, that is, to which process should the CPU be allocated, we consider out of all the processes that are ready to execute, we consider that process which has the shortest remaining time. The name is self-explanatory. Considering the shortest remaining burst time, we select that process, right, and assign the CPU to that process. And this is a preemptive algorithm. So this means that the control of the CPU can be taken away from the currently running process. So if there is a new process that has entered the system, or at any point in time, if there is a process which has a shorter remaining burst time, then the control of the CPU will be taken away, or we can say the control of the CPU will be preempted away from the currently executing process. So this is how the preemptive shortest remaining time scheduling policy works at a high level. And in this question, we are asked about the average turnaround time. So what is the turnaround time? Turnaround time, it's a very generic term that we use in our daily lives also. Turnaround time is the total time that a process spends in the system. That is, from the arrival time, from the time that the process arrives in the system to the completion time, that entire duration from the arrival time to the completion time, that entire duration is termed as the difference between that these two time instants is known as turnaround time. That is the total amount of time that the process has spent in the system. So this includes both the burst time, that is when the process is executing on the CPU, as well as the waiting time, right, where it is waiting for the allocation of the CPU. So turnaround time includes both the burst and the waiting time. And we are asked the average turnaround time. So all of these 4 processes would have some turnaround time. So we have to take the average of this. So this is the description of the question in brief. So now, having understood the question, let us now solve this. So in this slide, I have just summarized the key data that was part of the question. So this is the data for the 4 processes, the arrival time and the burst time. The key point is that we are going to use shortest remaining time for scheduling algorithm. And the thing that we have to calculate is the average turnaround time. So this is the important pieces of information that was part of the question. Right. So now let us understand, like try to execute these 4 processes and create the Gantt chart. And from the Gantt chart, we will be able to find out the completion time of the processes, from which we would be able to calculate the average turnaround time. Right. So here you can see I have written down the policy, that is SRTF, or short for shortest remaining time first CPU scheduling policy. So this is the policy that we are going to follow. This is the data for the process. So let us start the execution. So at the very beginning, at t is equals to 0, right, process P1 enters into the system. So you can see process P1 arrives in the system and it has a burst time of 10 milliseconds. So you can see it will ideally execute for a duration of 10 milliseconds. So we have not yet allocated the CPU to this process. It has just entered the system. So if you see at t is equals to 0, no other process is there in the system. Process P2 will come at 3 milliseconds, P3 will come at 7, and P4 will come at 8. So if you're talking about time instant t is equals to 0, then at this point we only have one process in the system. So there is actually no choice but to schedule process P1 on the CPU. So here the choice is quite simple, since there is only one process. So we will schedule process P1 and let it execute. So now the question is, till what time instant will we execute process P1? Will we execute process P1 for its entire burst time, right? We can see that process P1 has a burst time of 10, but we will not allow to execute it for its entire burst time. We will only allow it to execute till there are no other candidates in the system. So as you can see, at t is equals to 3, right? Time instant t is equals to 3, process P2 arrives in the system. And at that point, we have two processes in the system, P1 as well as P2. And now we have to again like run the algorithm and take a decision. So the decision that we had taken at t is equals to 0 might not remain valid at t is equals to 3, because there is a new process and it might be a better candidate. It might have a shorter remaining time, right? So in this case, when you're running a preemptive version of the shortest job first, that is shortest remaining time first algorithm, you have to execute uh, only till the point when there is another candidate in the system. When another candidate arrives, at that point you have to run the algorithm again. You have to evaluate the situation again and decide which is the best candidate, right? So we can see process P1 executed for 3 milliseconds. So its burst time, the remaining burst time for process P1 is now 7. It is not 10. The remaining burst time is 7, right? And for process P2, its burst time is 6. So this is the situation at t is equals to 3. Process P3 and P4 have not yet arrived. They will arrive at a later point in time, right? So at this point, that is t is equals to 3, the situation is that we have two processes in the system, and P1 has a remaining burst time of 7 and P2 has a remaining burst time of 6. So which one has a shorter one? Obviously, process P2 is a better candidate as it has shorter remaining time, right? So process P2, which has a shorter remaining time of burst time of 6 than P1, which has 7. So now we will schedule process P2, right? So we'll allow process P2 to run up till when? Up till another process does not arrive in the system. So we can see at t is equals to 7, another process arrives in the system, that is P3. So from the time instant t is equals to 3 to t is equals to 7, we are sure that P2 would be the only candidate which will be having a shorter remaining time, right? At t is equals to 3, when we made the decision, right, this was the situation that P2 had a burst time which was remaining, that was 6, and that was less than 7. And when P2 starts executing, its remaining burst time decreases subsequently, right? So it will always have a its remaining burst time will be always less than P1, right? And until there are only these two processes in a system, that is P1 and P2, we can be sure that P2 is the optimal candidate, because when we decided to schedule P2, at that time instant P2 was the optimal candidate, right? It had a remaining burst time of 6, and as it executes, its remaining burst time will decrease further, so it will always be less than the remaining burst time of P1. So that is why we can allow P2 to execute until there is another process in the system. So we can see at t is equals to 7, process P3 arrives in the system, right? So how much did P2 execute? P2 executed from t is equals to 3 to t is equals to 7, that is for 4 milliseconds. So that with these 4 milliseconds, the remaining burst time of process P2 changes from decreases from 6 to 2 milliseconds, right? And then process P3 arrives, which has a remaining burst time of 1. So now the situation looks like this. We have three processes, P1, P2 and P3, and these are the remaining burst times. P1 has 7, P2 has 2 and P3 has 1. Again we have to make a decision. Again we have to select the optimal candidate which has the shortest remaining time, right? And as you can see, the choice is obvious. The shortest remaining time is with P3, right? P3 has a remaining time, a remaining burst time of 1 millisecond, which is the least of all among P1, P2 and P3. So we will assign the CPU to process P3, and until any other process arrives in the system, that is till the point P1, P2 and P3 are the only processes in the system, we can allow P3 to execute, because that will always be the optimal candidate, right? So at this point, when we are allocating the CPU to P3, it is the optimal candidate. As you can see, 1 is less than 2 and 7. And as P3 executes, its burst time will subsequently decrease and it will always be less than P1 and P2. Right. So P3 executes and it actually finishes. Right. So actually at t is equals to 8, at t is equals to 8, process P4 arrives in the system. Right. So now at t is equals to 8, as you can see, the final process, that is process P4, arrives in the system, right? And now all the processes have arrived, right? So when P4 arrives at t is equals to 8, P3 has executed for 1 milliseconds, that is from t is equals to 7 to t is equals to 8. And that was the, so for process P3, the burst time, the total burst time was 1 milliseconds, right? So you can see process P3 has already finished. Now the remaining processes are P1, P2 and P4, and no more processes will arrive. So now when all the processes have arrived in the system, we know that the shortest remaining time first algorithm reduces to a shortest job first, right? Because no more processes will come and there is no need for more preemptions, because now we know that these are the processes in the system, these are the remaining burst times, and we just need to execute these processes in the ascending order of the remaining burst times. No more new processes will come, hence we do not need to do evaluations and preemptions again, like we were doing till now, because as new processes were arriving, the situation was changing and we had to reevaluate, we had to rerun the scheduling policy and see which was the best candidate. Now since we have global knowledge, that is we know all the processes that are there, so P1, P3 and P4, no more new processes will come. We can just schedule these processes in the increasing order of their burst times, that is remaining burst times. So this is a very important point, that after the last process has arrived, the shortest remaining time first algorithm reduces to a shortest of first. So this is important because when you're solving this question, it becomes easier to solve when the last process has arrived. You don't need to do reevaluations. So shortest of first, since it's non-preemptive in nature, now you can quickly finish the question. So now let's come back to this. So what is the scenario now? So P1 has a remaining burst time of 7, P2 has a remaining burst time of 2, and P4 has a remaining burst time of 3. So we can sort them in ascending order. So it will be P2, P4 and P1. So let's allow the P2, let's schedule the process P2, right? Process P2 executes and it finishes at t is equals to 10. So now we will be getting the completion time of all the processes, and using these completion times, we will be calculating the turnaround time, right? So after P2 is done, then P4 is the shortest one. So P4 executes and finishes at t is equals to 13. And finally, the last process, that is P1, executes. So P1 was the first to arrive, and you can see it is finishing the last, right? So this is how this policy works. So now we can see all of the processes have finished, and these are the completion times. So we have the arrival times and the completion times, and now you can use these to calculate the turnaround time. So the turnaround time is simple. Just subtract the arrival time from the completion time. That is, turnaround time is equals to completion time minus arrival time. And this is the column for turnaround time. And you now just need to take the average. So the average is 8.25 milliseconds. So what does this signify? This signifies that in this example, all the processes spend an average of 8.25 milliseconds in the system, with the minimum amount being spent by process P3 and the maximum being spent by process P1, that is 20 milliseconds. But on an average, the turnaround time, the time that is spent by each process in the system, is 8.25 milliseconds. So that is the answer to this question. So this is the answer, right? The average turnaround time in this case of these processes is 8.25 milliseconds. So this was an application of shortest remaining time first algorithm, right? So guys, this was it for this video. Thank you very much for watching. I'll see you in another video. Thank you.